All right, so let's go ahead and get started. We have a really packed day today, so we want to make sure to make the best of our time. Welcome back to AI Summer. We're on week 3, day 3, and in week 3, we're learning more about training models, and so that's what we're going to be continuing to do today. You already know me. I'm Charo Bell. I'm a senior data scientist here at the DSI, among other things. And also, my co-instructors for today will be Umang Chaudhry, a data scientist at the DSI, and Dr. Abby Petulante, who is a postdoctoral researcher at the DSI. For instructional support, we have Miranda Shirk. She's been answering your questions and giving us presentations, so she will be of great help. Make sure to ask her or direct questions to the chat so she can answer and help answer those questions. But otherwise, let's go ahead and jump right in. Oop. So this week, again, we have been learning about model training. We have learned about some really great platforms for helping us just chat with LLMs without having to write any code. And so we'll use one of those actually today. We heard about that from Umang. We learned from Miranda more about training models, what it's like to do back propagation, what vanilla LLM training looks like, or vanilla transformer training looks like. We've also learned a little bit more about how we can use synthetic data to help us as we are going through our training. Today, we're going to get into some serious coding. Okay, so regular coding, not overly serious, but we're going to get into some coding today. And today we're going to actually clarify some things that we've been talking about during the week. We're going to talk about the full scope of chat LLM training. We're going to draw some just little tiny minor distinctions that you will see disappear whenever you're looking at essentially any of the platforms that we've been working with. We're also going to talk about synthetic data. There have been some questions, and there's always questions about how much data do I need for training? How do I, train? How can I get this data? Do I have to do all this labeling? We're going to talk about synthetic data and the way that it can help us. And Umang will tell us a little bit more and show us and walk us through how to do some training of some state-of-the-art LLM models. And then Abby will tell us more about this new mechanism of training models called training by proxy. All right. Any questions before we get started? I got my nice chat window open. So if you have any questions, feel free to unmute, or you can drop your questions in the chat. All right, great. So let's just start, with talking about the kinds of LLMs that we use when we're either on OpenAI's website talking with ChatGPT, or we're on Gemini using that chat interface. Those models have gone through sort of a lot of training to become what they are. It's not just like one training and we're done. They go through many, many steps, and we can actually access many of those individual steps in different kinds of models. So essentially, there was this article that came out like years ago about what makes a dialogue model useful. And so this is a summarization of that, as well as some additional information for where we are today. So we've learned already, about pre-training. We learned that when we're training LLMs, usually we have a huge corpus of text upon which we do a supervised fine-tuning or self-supervised, where essentially we have all this whole corpus, and all we do is set up the data or those sentences or whatever that's in this corpus to predict the next token that's coming. So let's say that we have a sentence that is, I like cats. At any given time, I already know the entire structure of what that sentence looked like. So if I started with I, then the thing for the model to predict would be like. Once I have I like, then it should predict cats. So that's how we can do generally our pre-training, but we do a lot of that on a lot of data. The next step that we go through is actually the same thing, except for we change the data set upon which we are training. And this all falls under something that people like to call supervised fine-tuning, where we have actually given the model very specific answers as to what we want. So that is a little minor linguistic kind of jargon kind of moment where we are usually thinking of pre-training as, yes, predicting the next token, but that's just on this huge corpus of text where we're doing self-supervised training. And here we actually have answers that some human being or maybe some synthetic LLM is helping us to generate. So in supervised fine tuning, what we have are different data sets. Again, we're still predicting the next token, but the data sets now are different. And so the first data set that people tend to use is an instruction fine tuning data set. So whenever you're able to say, hey, model, can you, so here's a paragraph of information, can you generate an email from this? That is an instruction. And so we train models so that they don't just like keep on just predicting the next token, they actually predict the token in an instruction-based way. So now it actually creates this email from that paragraph that you gave it instead of just kind of continuing on with whatever you were previously saying. A second kind of data set that is used during this supervised fine-tuning phase is the safety fine-tuning data set. And basically what that's meant to do is it's meant to help to train the model so that it gives responses that aren't harmful, aren't malicious, are actually helpful. It's about having the model respond in ways that are appropriate, that we want. So a lot of it is minimizing harm and then increasing helpfulness. The last kind of data set that we kind of have been talking about throughout this week and throughout the summer is this function calling fine tuning, where we are trying to help models learn what we need from them when we're going to try to call a tool. So remember that with function calling, usually what this model is doing is it's looking at some information and it's trying to determine the parameters in which it should return for you to call the function. And so there are data sets available to help these models actually execute this function calling fine tuning. And they have to go through all of these types of training to be able to do these different types of things. The last kind of training that the models usually go through is about human preferences. So there are times that we want there is another kind of training that they also go through. Sometimes people call it like chattiness. So it can be like conversational sort of agent instead of just like telling you something. But in terms of human preferences training, that is where some people or some model has gone through and it said, this is the preferred response to this kind of statement, and this is a less preferred response. There are many ways to do this. In our early days of human preferences training, we were using something called reinforcement learning from human feedback. And developers still do this. It's absolutely valid. And there are other mechanisms now for training models, which has a different kind of approach. So reinforcement learning from human feedback is reinforcement learning, but that has also been cast into some different ways of interpretation, which basically make the training boil down to a certain kind of classification. And you'll find that under something called DPO or PPO. So again, just if you're a graphical kind of person, so our models go through lots of training to actually become chatty or chatbots. Here we have the pre-training, again, predicting the next token. We're learning about grammar. We are learning about how concepts are together. Sorry, I'm not sure if you can hear that in the background, but my pets are having a disagreement. I think they disagree about maybe the order of some of these fine tuning steps, which is fair because some of them don't. Some of these in particular, they're mixed together. They're disagreeing, you know what, they'll come to an answer. But so we have our pre-training step where we have huge training corpuses. We do that in next token prediction. It's learning about concepts, it's learning about grammar, it's learning about general things that occur in the data set. Then we have the supervised fine tuning where we have a data set where someone has set out the actual answer in which they want the model to like state. So they state how they want the model to follow instructions. They state what they think non-harmful or safe responses are, and they also state what the outcome should be for function calling. Lastly, we have this human preferences training so that the model learns to actually respond in ways that humans prefer. So these are the general steps that you see to get from straight LLM. So straight LLM, so if it's pre-trained only, and you're using something like LM Studio or you're looking on Hugging Face, sometimes you'll see these pre-trained only models called base models or just LLM. So Gemini LLM or Gemini Base, or not, you wouldn't see Gemini, but like Gemma Base or whatever have you. So they'll be reflecting this phase of training. if they've gone through some level of supervised fine tuning, particularly the first instruction fine tuning, you'll see them called instruct models. It's sometimes unknown unless you read the model card exactly what kind of instruction or supervised fine tuning that they've gone through. Usually it will be following instructions, and often it is now the later models, it's function calling. Some models, when they are available for researchers in particular, sometimes the instruct models do leave off these safe or non-harmful responses so that researchers can look and see the effect of how you can train these models to have the responses that you actually want. But if you see a model referred to as an instruct model, it's been through some set of these steps, and it's usually going to be at least following instructions. Once you see human preferences, so once the model has gone through this phase of human preference training, often you might see that one called like the chat model. So it's gone through all three of these steps. And so that's when you tend to have a more full chat LLM, although sometimes you really do have to read the model card to know exactly what set of training that this model has actually gone through. So we're actually going to just transition really quickly over to LM Studio. I think Umang introduced this to us, and so we're going to use the tools that we have available to us. We do love tools. They help us to do things quicker and understand what's going on. So you can just watch this if you want to. I can give you a quick second to open LM Studio. However, I have already downloaded some models, and those models may take just a little bit of time to download, so feel free to just watch this. So this is LM Studio. And so what I'm going to do is I am going to go to this playground. If you were, yeah, they're still having that disagreement over there, over that safety, that fine tuning. All right, guys, we'll see. We'll have to, help them with that. But anyways, so I've downloaded these different LLMs. And so here we're in the playground. If you were at the training yesterday, we did a lot of playground stuff. If you're here on week 2, we did also a lot of playground stuff. It literally helps us to play with these models. You can see here now some of the different naming that we apply to the models. So this is a model in a specific format from Hugging Face, and it's Llama 2. And you can see that it doesn't have any other kind of special things added to it. It's just Llama 2 7B. This one is a little bit different though. We can see that it has it has a different context length potentially. And then also it has this instruct in the name. So actually I'm gonna reload this one too. And here you can see one last modification where we have this chat bit also added. So we're gonna reload this one. So now these models are actually pretty small. Umang was telling us that when we have the quantization, so reducing the size of any individual number in the LLMs, when you quantize it a lot, it makes the model fit on your GPU, but sometimes performance is a little bit less than what we would want. And so these models are the most quantized that I could get them so they could run on the GPU without Zoom dying. So if you see some, answers here that are just a little bit not the best, that's why it's the most quantized version, although it's still pretty good. All right, so a little bit more about LM Studio. If we click on any of these, we can see some of these parameters. So for example, the custom instructions, it's a little bit different for this one because this is our LLM. So here you can see that I've already actually pretty much tried this just, to see. And so here what we're going to instruct each of these models to do is to respond to this prompt, which is write a headline for a pop magazine news article about a new type of cat discovered in Arizona. If you haven't noticed yet, it seems like the data science team, we love to talk about cats. Don't know what's going on with that, but that's who we are. Okay, so what this is an instruction. I am asking for this model to do something very specific. So this is our regular base llama. And you can see that actually what it's doing is not responding to the instruction. It's just kind of continuing on with whatever it wanted to say. So it thinks that I wanted to just keep saying more in the sentence. And then so it just continues on with what it thought that maybe is great to say afterwards based on its sampling and all that great stuff that we learned about. So here you can see this is doing the pre-trained behavior. It is just predicting the next token as we go along. This one in blue here, this is our instruct model. So and sorry, I can't make this much bigger. But what we can see here is after the instruct, it actually follows the instruction. So unmasking the mystery cat, like this is perfect. So this is definitely a headline for a pop magazine. Here it is like super, this is the chat model. So this is base, so pre-trained only. This is some level of instruction. This is the full chat training. And you can see it, you can see the chattiness, which is sometimes trained into the model as well. But you also see that maybe this is a preferred response. Like this is pretty like, it is a news headline, but this would take into account news headline for a pop magazine. Meowsing discovery, how delightful. And so you can kind of see, one, it's chatty, but two, it does kind of take into the preference of wanting a pop magazine news headline as opposed to just like a news headline. All right, and so those are just a few examples. You can always try on your own now that we know more about LM Studio. I'm also just gonna casually unload these just in case. So basically I took that out of my GPU. And so any questions about that? There are some really great articles about this on Hugging Face, and also Archive has just like some excellent summarization articles. I mean, just better than I don't know how I haven't seen them before, but they're just absolutely excellent. Any questions? All right, moving right along to another screen that has a lot of little tiny words on it that perhaps you won't be able to see very well, but I can, let's see, actually, can I highlight this? Nope, but I can highlight that and put it in the chat a little bit later on. But this is a summary of some of the open source models and the training that they've gone through. So some of these open source models, we might not really call like LLMs or chat LLMs in the sense of how we talk about them today. So we can focus our efforts in looking at this towards this llama. So I think this is llama like a 1. And then this here would be llama 2. Okay. So what we're particularly interested in is the pre-training data size. And even if we just look straight down this list, looking at the number of tokens, these are huge numbers of tokens that these models are trained upon. You can also see like they take a lot of steps to train the model. It takes a lot. So you can also see other stuff on here, just flat out interesting. But you can see here that even with Llama, this is 1.4 terabytes like trillion tokens / data. And then for Llama 2, we have 2 trillion. That is a lot of tokens. And so we understand that if we want to pre-train a model, that we're going to have a lot of diverse data. And also, again, I'll put this in the chat, but you can see the kinds of data that these models are trained on. It's not just one thing. Usually it's like a set of a lot of different data sets so that the model can learn the wide span, even during pre-training, of the things that it needs to know to support being an LLM. We think about that second step, okay, of fine-tuning or model chat LLM development. We think about the instruction fine-tuning. And so what we can see here is just in general, although we can't really, these are not exactly the models, maybe alpaca for sure. Alpaca comes from llama and is trained on it's trained for instruction fine-tuning. And so here we can see that this is a significantly lower number of, so this S means samples. This is a significantly lower amount of data upon which it was trained. And why is that? As you move further into the training process, you already have very solid foundations from the previous steps. So during this instruction fine-tuning, the model is really focusing on learning instructions and learning how to do safe responses or learning how to do function calling. So the data set to train them can be smaller because it already knows lots of things about whatever language or that you're interested in. And I can put this also in the chat. So I said all that to say, if you are sort of wanting to train more after that, so you have some, even if you have a chat model, actually, you can create some synthetic data upon which to train models. And this is a completely normal thing to do. So here, this is an article from Hugging Face, literally March 20th of this year, where they're talking about how they created this synthetic data set to build something that would be similar to Microsoft's 1.5 model. And so that thing now, this hugely synthetic data has been called Cosmopedia. So thing that people do, even Stanford's alpaca, which I mean, just blew onto, the scene and everyone was really impressed with it. Something that they did was that they created the synthetic data set of instructions specifically using a model like an LLM already to create that data. And so this is important for you as well. If you need lots and lots of data because you want to do like function calling or something, and you're just not going to sit there and write all of that data, you can use existing LLMs, maybe a set of existing LLMs to help you generate that training data. And it doesn't really need to be a huge amount, because at the end of the day, if you start from something that has already at least gone through instruction fine tuning or function calling fine tuning, then you don't need as much data to train that model to do exactly what you need it to do. So now we're gonna try it. Okay, so we're gonna use LangChain because that's what we're familiar with, but there are other platforms that we could use to help us as well. And so how this is gonna work is we will talk about how you can create a synthetic data set from using existing LLMs, but we're gonna talk about it from the perspective of as if you needed to just like do this, and maybe you were on your own. So we're gonna see what it's like to try to develop something on our own with, let's say, for example, me, like the data science team isn't here. So when you're by yourself, we need to make it happen. All right. So unfortunately, learning two things at the same time, but in the interest of time, we're gonna try to do that. So if we go to langchain.com, we might think that that's a great place to start, which would be fair, because it is a great place to start. And so we might start here. You can see the docs was already highlighted. And so we might start by just going to the LangChain documentation. So we're excited. We've seen this before. We've actually seen this actual graph before. We're pretty pumped to see it. We're used to it. And then we might say to ourselves, all right, well, let's just see what LangChain can help me with. I know they have lots of notebooks here. They have lots of description, but let me see, I want to do synthetic data generation. Let's see if they have anything already pre-prepared. So at least I can start from somewhere. So in that moment, we might scroll down and we go, well, let me just at least look at something. Let me see. All right, well, this is pretty much the sidebar. We might go to tutorials because maybe there's a synthetic data generation tutorial. So we might look down. One, we're kind of moderately distracted by the basics because all of this looks really good to review and it looks like things that we're interested in, but we're focusing on synthetic data generation. We also will try to scroll past this, but our eyes will be caught by the fact that we're interested in RAG, we're interested in conversational RAG, we want to know what query analysis is. We tag that in our brains to come back to it. We get a little bit lower and we read a little bit, okay, all right, we see some specialized tasks. Generate synthetic data. That looks really exciting. That looks like something that, that's what we want. So now that we see this tutorial, we're pretty excited. And so we click on this. And so we look and see what it's going to try to tell us. We always love sidebars because it's going to go through the rundown of what we might expect to see. All right, this sounds like a bit right. We might even scroll down. All right, this is sounding right. This is something that we've seen before. This is our schema in our mind. We're saying, all right, I've seen that. I see some examples. That sounds about right, because if I need new data, that means that I'll probably need some examples to show the model. All right, prompt template, we know about that. We've seen what that does. It sounds like data. All right, this sounds like what we're looking for. So in our minds, what we want to do is we see this open in Colab button, which we're so pumped about because we've been opening things in Colab. We might go ahead and click on it. We have this moment where we're like, okay, something weird is going on. Oh no, we have this error. Terrible. So something that we do know is that LangChain is moving from version 1 to version 2. And so because of that, I'm going to save you just a little bit of time. If this is also in version 1, but so I'm going to navigate really quickly, although I'm going to save you the link. I'm going to send you the link in the chat. But This is just kind of like a remnant of the fact that they are moving like over. And so this link probably just hasn't yet been updated yet. So very quickly, we go to the version 1 docs. We might go to more, and there we go. Synthetic data generation. I'm just going to open this real quick, and I'm going to send that on to you. All right. And again, so if you need, like you don't feel like typing today, even though you won't be really typing that much because we're starting from this template. If you just want to see the answer, you can go to the AI Summer repository, and it will be there. Like there's the solutions for day 3_3, and it'll have everything that you need in it. But otherwise, you can pretty much just run everything that we have here, because we, again, are in this moment where we are trying to figure out how we can make this happen, even though we are on our own. So here we might read a little bit about this. Basically, it's going to tell you really delightful things about why you might want to use synthetic data. Synthetic data is also, I mean, fantastic for whenever you have proprietary data. Maybe you want to actually put this proprietary data on OpenAI because you want to submit it so it can do some kind of processing, but you're not sending proprietary data up there. But if you have synthetic data that looks just like that proprietary data, then you can use that to help you instead. So now we are familiar with Colab. We will start by running these cells. So we're going to click this run button. We're going to run anyway. As it's running, we're going to look with our eyeballs and just inspect some of the things that it's saying to us. Something to know is that I'm using something called Colab Pro. Colab Pro, it's like, I forget how much it is a month, but it helps with coding. And so you can see this thing over here. It says Gemini. Gemini is another LLM, a chat LLM, that can essentially help us while we're coding. And we just kind of open that on up and we ask Gemini questions. So whenever we're confused, this is something that we can go to. Something to keep in mind about the way this is implemented now, which is super interesting, is that you only have 400 characters, I think, to put in there, which is that's a limitation for how I generally prompt when I'm coding. And so sometimes you will need to open up a different kind of LLM, which would be helpful. So anyways, if we're confused about what we're looking at, we can always use that. So one, we're excited because we have already, done our pip installs. We got our order from Amazon. Now we're making this available to ourselves here. And some of these things are looking familiar. So we remember Chat OpenAI. That's something that we've used in the past. We remember prompt templates. Some of this other stuff is like blowing our mind. Like we vaguely remember Pydantic V1 and base model. We remember that from when we were doing our function calling. We wanted structured outputs, so that's okay. Few shot prompt template, looking unfamiliar. All this experimental, unfamiliar, unfamiliar. All right, so now we're just like a little bit concerned because some of it is looking unfamiliar, but we're just going to move forward because it's telling us that this is how we should do it. So then we read this a little bit more. We're looking at this. It's telling us that we should create this schema. And again, this is familiar to us because we have been through a whole 6 hours of training on LangChain. And so in 2 hours on one particular day, we talked about this for probably 10 minutes. So we're complete experts, but we think back to ourselves and we remember, okay, whenever I want to create a structured output, I use this specification, this schema, which essentially says what I want the fields to be, what kind of type I want them to be. And if I wanted to, I could add information, so specific descriptions for each of those fields. So we're going to run this one and create this one. So now we have this class medical billing, where if something were to add medical billing examples or synthetic data, we would want it to have each of these fields. We want a patient ID, name, all this great stuff, and we want each of these fields to have these specific kinds. So we would want patient ID to be an integer. Interesting, actually, we'd probably want that to be a character. That's okay. A set of characters, that's all right. Or a string. We would want this to be, and we would want these to have these types. So now it's telling us we need to create some sample data. Okay, so that's fair. We're asking the model to create us some synthetic data. It probably sounds good to us in our minds that with our when we're prompting the model and trying to get it to do stuff for us, it's good to give it examples, especially if they're kind of maybe new examples that the model wouldn't have seen specifically. So here we're trying to make this medical billing fictitious set of records. And so something that we notice is that it has a few different. So these are 3 examples. It's telling us that we need to set this to be a list. And then these things in here are like kind of JSON specifications or dictionaries where we have the layout as the name of or the key name is going to be example. And then we have this big old long string of the example output that we want to see. So we have our patient ID with this number, patient name, and all of these things up here. We gave it 3 examples so that the model will be able to use those examples to generate synthetic data. So in our minds, we're feeling kind of confident. It's feeling good. Then it asks us to make this prompt template. And so we are just following along in its example to understand what to do. So we look at this prompt template. It's looking kind of familiar. In class, we really have never specified this input variables, but what we have specified is something that looks like this, where we would expect that example will be filled in by something. And so we're calling that OpenAI template. Great. Then we have this other thing that we've never seen before in our lives called few shot prompt template. But we think in our minds, we're like, all right, well, prompt template allowed us to just put in some information or substitute it in specific things. We know from our learning that few shot means that we give it a few examples and then we ask it to do something based on those examples. So in our brains, we say to ourselves, okay, a few shot, it's going to be like a prompt template, but somehow it's probably also going to build in the examples that we need. So we would be exactly right about that. We look at the parameters that we need to pass in. There's something called prefix. We don't even know what that is. We might expect to see examples because that's what few shot prompting is. We see the suffix. We don't know what that is. We see these input variables. We understand that that's something that we probably need to invoke, even though we also kind of don't know what that is. And then also we look at example prompt and we're not understanding why or what that is, but we run it. So when we are not understanding, or we're just kind of trying to take a second and understand, this is why we like developer-friendly documentation, because it will explain some things to us. So this is really nice. It talks about what prefix and suffix are. It contains guiding context or instructions. We're not sure whether how that affects us, but we read the rest of this and maybe we're feeling a little bit better. Also, we can just take this and maybe we start using Gemini. So I am developing, trying to generate synthetic data using LLMs in LangChain. The code is as follows. What does, oh, see, this is what I'm saying. It's too short. We're going to even shorten that up even more. What does this do?
Sharo, could you open regular Gemini because it lets you, it doesn't give you that 400 character limitation?
Absolutely. Absolutely. That would definitely be the way to go. Sometimes, we have a little sidebar. We might be able to make it short. For sure, we will see an example of maybe opening up ChatGPT or Gemini. That is an excellent suggestion. I'm 100% right on. I'm right there with you. So here, maybe we're concerned about what this does. And so it tells us more things. So it's exactly telling us what things are. We can read through this and feel kind of confident. Something that I like about Gemini, and I don't have any justification for this, except for the fact that this is here in Colab Pro. Something that I like, and I think that I like about it is I have just this feeling that Gemini will be really good with whatever code that you need to write, because it would have seen a lot of code, because this is Google's Colab Pro. And you might expect that Google has used these kinds of notebooks, specifically Jupyter notebooks, for training. And so that's just a suspicion that I have, but I have noticed it a little bit more, where this particular model, Gemini, is really, it's pretty good with the things that people normally do in Jupyter notebooks. So here it describes our prompt templates, and it actually provides a little bit more information above and beyond. Oop, I'm going too far in my time, but it provides some more information above and beyond what even we see in this notebooks. It says the prefix says what comes before the example, suffix comes after, and then what the example prompt is the template to be used for each of your example, even though we are kind of still a little bit iffy on what that actually is. So now what we might do is, we are very used to like just looking at this and then actually seeing what is in these variables once they're created. So we run this, and then we might create a new cell. Actually, we're going to create it here to inspect actually what is like going on. So one thing that we sort of know is the input variables, they have to be defined whenever you invoke like something. And because this is a prompt template, we know that we can call invoke upon it. So what we can do is just do prompt template. And this is another thing that we love about Colab Pro. It's going to help it just predict whatever else that you might write. So here it's going to try to format prompt. I don't know if that's what we want to do, but it looks like that's something that we may be able to do. It's not always going to be right, but a lot of times it is. Let's see what happens if you write the actual invoke part. Oh, it's not quite sure. So we're going to help it a little bit and help ourselves. We know that we need to specify subject because that's one of the input variables. We're just going to say this is, oops. This is where the subject goes. And then we're going to do extra. This is where the extra goes. And we're just doing that because we want to see what this prompt template is going to look like after we have like done anything with it. So we can run this. We see that this is what it is going to look like, which might be a little bit hard to see. But something that we do know is in the past, we have just written dot text whenever we see things like this. So we might say, all right, well, let me try that. And great. So here we have what it will look like. One last thing we might do, because printing is a little bit of a different experience. It kind of resolves these like values so it looks like something we can actually see. So we're actually going to print this whole thing. And we see that this is what the prompt template looks like. So this thing that we've defined, this is what it's going to end up looking like. This is a test about generating synthetic data. This is whatever subject is. So if we want to fill this in with something else, we can change subject. So we might change this to be medical billing. Then we see how the examples are filled in, and we see the role of OpenAI template because it's just where the the whole text of the example. This is one of the examples, another. So that's made it all into the prompt template. We also see the prefix, which is this. This is a test about generating synthetic data about blah, blah, blah. We also see the suffix, which is now you generate synthetic data about, and then we see that this is the subject. Again, and then we see this is any extra information that we want to put. So that has told us how we can actually use this if we need to change it in the future. Delightful. So now in our minds, we see, all right, so now it's going to tell us how to generate the data. Great. We look at this thing that we've never seen before, create billing, OpenAI data generator. We can hover over, we can see what it wants, but generally what we're going to do is just follow what it said. So what we're going to do is first we're going to look at this and we're going to say to ourselves, chat OpenAI, delightful. That sounds really good. Oh, and it's not letting me hover. That's okay. We're setting the temperature to be 1, meaning probably we're going to get a lot of creativity. and it's passing in that prompt template that we just had. Great. That sounds good. So what we're going to do is we're just going to go ahead and run that. We're going to have a moment of absolute panic because we're going to think to ourselves, oh my gosh, the documentation is wrong. And so what we're going to do is we are going to come down here and we're going to read what's wrong with it. It says one validation for this thing. It says did not find OpenAI API key. Please add an environment variable which contains it or pass this as a name parameter. Interesting. We can click this explain error thing. Let's see if it helps us. Oh, it's thinking. So fair, this is a good suggestion. Basically what it's saying is if you could just add that into this call, that'd be great. And here is some code that would allow you to do that. Wonderful. This is actually what we're going to end up doing, a piece of this. So I'm going to just take this relevant piece. And we're going to have this moment where we think back to how we use this OpenAI key in the past, because we've seen it in lots of notebooks where there was something else here. And we think, oh, I remember that time where we were struggling getting those API keys set up and we clicked on this key thing. All right, I have my OpenAI key, but oh, to access your secret keys in Python, then I need to do this. And this is what I've seen in a bunch of notebooks, so I'm going to do that. So we'll copy that as well. Remember that this part is where we got the secret from, or we just go back to the notebooks that we've seen already and we copy this little bit. And then we know that this and this generally match because this is this. So we'll run this. And then we'll rerun this. And here we see we have gotten our result. Excellent. It ran. Great. So now this is the generator that's been created. And now we will actually just follow their instructions. They have this generator. They're calling you to generate on it. In our minds, that makes sense because you need to generate stuff. They're passing in those fields that we saw before, and we're going to go ahead and run that. It tells us that this will produce 10 synthetic billing records, which is exciting. The output will be a list of medical billing pydantic models. Great. We don't see it here and they haven't printed it out. So let's go ahead and look at synthetic results. So this is amazing. It looks like it did what we wanted, which is super great. And we're super pumped. We're like, great, we have our synthetic data. But then we say to ourselves, okay, but what is a list of medical billing pydantic models? Like, what do I do after that? So then what we might say to ourselves is, all right, I need to make this into a CSV or something that I can actually use. So this is where we take the suggestion that was given about not using this 400 length context, but going to some other platform. So what we might do, and sorry, team members, I am going a little bit long, but I'm going to try to finish up real quick. So here we might go to ChatGPT and we might try to prompt the model to help us with this. And here again, this is the moment where you want to give the model as much information as you can. So it's not just like answering out of a void. So I am doing synthetic data generation using LangChain in Python. I have defined an output schema. And so we're going to just take that output schema that was defined. Then we tell it what we're actually looking for. So after the synthetic data is generated, the results look as follows. And so here, I'm just going to straight up take these results, copy them, the whole thing. Just give it all the information, shameless. How do I convert this to a CSV? So here, it's going to help us out. Oh, it's kind of freezing a little bit there. Great. It's saying you should use pandas, which is the best possible suggestion. So now it's telling us a lot of stuff. It's chatty. So here is what we had. This is what we have. If we wanted to directly just try this out, we could copy this entire code, but we know that this is what we already have somewhere in our notebook. We know that this is something that we already have in our notebook. Wow, it's really just focused on saying all those things. But now what we want to do is do what it says. So it is called this thing right here, data. And so here it's making this suggestion to us. And so we're just going to use like this part. Something that we're keeping in mind when we're developing is that it has called this example data because we didn't tell it what the variable name is. And so it's likely that we will have to change this as well. So then we come back to the code. We paste what it says. We see our little squigglies. Thanks, Colab. We know that this is what our data actually is. So we'll replace this squiggly. This is another squiggly where it's saying that's not defined. But remember, ChatGPT told us actually what we need to do is do this. Import pandas as PD. So we'll add that too. Our squiggly should go away. But okay, and there we go. It then says, all right, so that'll be the data frame. It says to CSV, index false. Great, we're just going to run it. So it seems like it printed this. In Google Colab, we can see where things are, where we have this medical billing data.csv. And there it is. So we can download this before the end of our session, before we close this. Otherwise, this will be gone. We want to download this, download, if that's something that we actually want to use. So there are lots of other things that we can do as well, but in the interest of time, I will have to leave it here. Do know that when it comes to data frames, there is lots of functionality that you can do. Maybe if you want to generate with AI, you can have it, maybe create a histogram from something that's in here. You can just, I don't know, create a histogram. I don't know, that might not even work because that's not even well specified. We'll see what it comes up with. But there are lots of, we could just try it. Oh, and there we go. We can, and it actually did all the things. So this is just another way that we can just have things help us. All right. Okay. All right, other questions? I see a question. Okay.
Have you found that using either ChatGPT or Gemini creates a bias towards assistants that are created by that platform?
What do you mean?
If like here you just asked it, help me do this, and it suggested Panda. And I don't know, like I'm just generally asking, do you find that the various platforms will have a bias based on who developed them, or if it's within a same parent company?
There can be some really funny things that happen with models. And it really just depends on sort of where they are. I think I mentally just sometimes think like, okay, well, Google does all of these things. So obviously it has all of the data for these things. So it'll be good at blah, 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 blah. And sometimes that is correct. But pandas is something that is specific to all of data science.
Okay.
But Colab notebooks are used a lot in data science. So you would expect that if models were trained based on these Colab notebooks, they would maybe, go to data frames first as a like way of creating CSVs instead of doing like something else. So I don't know that I observe it. I think those are just my own like internal suspicions. But I will say something very funny that I just find it utterly hilarious, and I don't know why. Is that ChatGPT, as we know, it's built on the OpenAI platform. So the OpenAI API is the way that we interact with it programmatically. The thing is that before, I think, recent updates, OpenAI had a specific version of their API that differs from the one that they have today. And sometimes if you ask like ChatGPT, even GPT-4, about writing code for OpenAI's API, it'll write code for that version 1 and not the version 2. And so it won't like write it correctly, and you have to do like a lot of prompting to get it to use any of the version 2 API. And I just think that's really funny. Like OpenAI, I mean, it's like it's your own platform. As they say, it be your own people. So yeah, like it just generates this code that doesn't even work for its own platform. But yeah, I'm not sure. I haven't seen it like have bias, but I do like to think of using LLMs where my expected belief that their strengths will be. So for Colab, like I do expect to see a strength in things that you do in Colab notebooks in Gemini.
Thank you.
That's a good question. Other questions? I thought I saw another.
Yeah, hi, Charu. What would you call the synthetic data generator that you created in the end? Would you call that like an agent, or would you call that a like pipeline, or is there anything?
Oh,
I
sorry,
don't
go
know
ahead.
is there anything that I can kind of call that? You've created something that generates data. I know that, but like in the LLM verbiage, what would you call that?
So that is a moment. So I had a very similar question as to what it was, like literally, what is it? That's a good moment for the API because it is open source. You can go and look and see what it is. And really, it just appears to be like, the chains that we created, it's just a very specific ordering of components in a chain. So essentially, they've abstracted the need to write your own components, like a specific kind of like parser or a specific kind of like input that you need to do. Like they have abstracted that so that you don't have to do those things. You can just focus on the specific things that you want to pass in, but it's just like a regular LLM chain with
LLM
structured
chain.
out.
Okay. It's a LLM, it's a Lang chain LLM chain. It's a Lang chain thing.
So this specifically is a Lang chain thing because they have ordered the things. So like this,
Okay.
it is this thing right here. It is a synthetic data generator. If I could remember how to import it, I could show it to you. But essentially, like if you get something that I really love to do, and I think is funny, is like if you really get like aggravated and you're trying to look at the documentation like really hard. Let's say we're trying to look at base model. Sorry, I'm typing wrong. Which is something that we use really far above. If you do 2 angry question marks and you run that, it'll show you the code on this side about what it actually is. So if you need to know exactly what it's doing, it is like literally like the actual source code of the implementation. And so you can look at it and inspect like what is actually happening.
Okay.
But we just have to know what exactly is the name of like the thing. We could also try it. I'm sorry, I'm going. We could try it on this one. It's just another one of these. Up here, you can see exactly where this is coming from. So we can import this one if we want to and double question mark it. But essentially, it's just like, there it goes.
Okay.
And there goes the chain. And we remember essentially structured output chain. There's the schema. It's something that abstracts information. So it's like the developer doesn't have to write like these very specific things. But you also do in LangChain have the freedom to write those specific things if you want to. But this is something that can kind of accelerate you, or if you're just trying to get something on the page, like this is a way to approach it.
Okay.
All right. Well, I have gone way over time. Sorry, Umang and Abby. Do we want to take a break first and then go into Umang and Abby, or Umang, would you like to go before the break?
I think I'm fine taking a break. I only need about 15 minutes, maybe 15, 20 minutes. Abby.
Yeah, I think a break now. Sounds good.
Okay, that sounds good. Let's break until 10, so for 5 minutes, and then we'll come on back and hear about training models in the last half.
All right, let's get started. Let me just share my screen. So what we're going to be looking at next is how we can actually do fine tuning of a large language model. And the good thing is, to get started, you don't really need too much compute. You can probably do this with the sort of free tier that Colab provides you with. So we're going to be taking a look at 33P FD-Gemma. What this notebook basically is parameter efficient fine tuning of Gemma, which is the latest open source model provided by Google. So we're going to open that right here. As always, since we're working with large language models, it's always a good idea to sort of have a GPU in the mix to keep things quick. I'm currently connected to an A100, which is the best GPU that I can get at the moment. And you might not have this if you don't have the paid. I'm on Colab Pro, so I get this, but on the free tier, I think you might just get a T4, but that should be good enough. The first thing that we're going to want to do is provide our Hugging Face token. As a reminder, if you go to Hugging Face, just go to Hugging Face, and you land up here, you want to first go to Settings, and then you want to go to Access Tokens and copy whichever token is a write token and paste it right in here after you run this code chunk. Let's see, we have a question. Okay, Sharo, maybe you can answer that. And then I've already run this notebook because it does take a minute or so to get through some of these things. But essentially what we're doing next after providing our Hugging Face token and authenticating ourselves is installing a bunch of packages. Just so you know, the -Q means quiet. That means it's only going to print out one line for each install it's going to do rather than the thousands of lines that it actually prints out without that. U just means upgrade, and then I'm specifying specific package versions so that this code remains consistent. And if Google or LangChain or Hugging Face happens to update their code, this code will still continue to work in persistence. So once you have all of that installed, let's talk about what we're trying to do today. So for this specific example, we'll be fine-tuning the sort of base model Gemma on the English quotes datasets. So that is a dataset provided by Byret, which is essentially just a couple of quotes with the author and a couple of tags about that specific quote. So for example, Be Yourself, Everyone Else Already Is Taken by Oscar Wilde. And you can see that it has a couple of tags that might contain things like where it's from and just the general themes that the quote might be talking about. So what we want to do is essentially have a model that is instruction fine-tuned, that when you provide it with the beginning of a quote, it completes the quote and provides you with the name of the author. So we're going to just access Gemma 7 billion parameter. So that's just Google Gemma 7B. That's the model ID. This is how we know that it's the base model. It doesn't have anything appended to it. If this were to instead say 7BIT, that means it's instruction fine-tuned. And the same goes for all of the Gemma models. They seem to follow a very similar naming schema. It could also say IT chat, which just means that it's optimized to be a chat model. But at the moment, all we're seeing is a next token prediction sentence completion sort of model. So we've given the model ID. We're going to, again, load in that bits and bytes configuration that we saw yesterday, which is just essentially loading a smaller 4-bit version of the model, just so that it fits in our single GPU. We're going to specify the tokenizer. We're going to use the auto tokenizer class from Pretain, give it the model ID and our Hugging Face token. And using the model ID, it will pull the appropriate tokenizer and also the appropriate model with the quantization configuration and then mapping it to our GPU. So it downloads all of that. This might take a second. I think it took me a minute and 5 seconds to download the entire thing, but it is about 10 gigabytes worth of stuff. So it might take a second depending on your internet connection. If you don't have access to a GPU, you still can inference on these models. You cannot train, but you can inference on these models by just calling auto model for causal LM from pretrain and not providing this device map. This device map is what's telling the code to put it on a GPU, but if we don't provide that, it just puts it on a CPU. And now let's just see how Gemma does on this first task without doing any sort of fine tuning. So we give it the start of a quote where the quote is imagination is, and I'm saying the device is CUDA, which is just the GPU. The inputs, I tokenize them using the tokenizer and then send them to the GPU. And then I take the model, I do model.generate, give it the inputs, and then just print the output. And I see imagination is more important than knowledge. It got the quote right. It also got the author right, Albert Einstein, but it is moving forward and saying, I'm a creative and curious person who loves to learn. Probably just because it doesn't know that's where it needs to stop. It's not really following any instructions. It's just thinking, okay, after Albert Einstein, it might make sense to type, I am a creative and curious person who loves to learn. So questions about this so far?
And so is that basically about 20 tokens? This
Yes.
whole thing? Okay.
Yes.
So it didn't know, it just kept printing until it hit 20 tokens and then it stopped.
Exactly. Yeah.
Okay.
Other questions? Cool. So moving forward, let's take a look at the data that we want to use and also the training setup. So first, we're just going to provide this environment variable. 1B is just weights and biases. It's another package that allows you to do a little couple more fancy things while fine tuning, but we're just going to disable that for now because we're not doing any of that. But first, let's take a look at the model itself. So if you were to print out the model, this is what you kind of receive. So we see that it's Gemma, it has the embedding layer, it has a bunch of linear layers, it has the attention and the rotary embeddings, and then it has a couple of more layers and activations. So basically what this is telling us is this is what the model kind of structure actually looks like. And it's important to know what this looks like because when we're doing LoRa, which is what we will be doing today, our parameter efficient fine tuning method will be LoRa. We want to know what layers to kind of do that training on and what adapters to add. And usually as sort of a rule of thumb, we want to do that on the linear layers. So all of the linear layers that you see here, the Q proj, K projection, V projection, O projection, these tend to differ a little bit depending on the model that you're looking at. But what these specific layers actually do, you can kind of read in the sort of model specification paper. But generally, no, according to the LoRa paper, they say that we find that the most critical LoRa hyperparameter is how many LoRa adapters are used, so how many of these layers in total, and that LoRa on all linear transformer block layers is required to match full fine-tuning performance. Basically, this is saying that include all these linear layers for the best tuning results, to keep it simple. So we're gonna wanna include all of these linear layers right here. And so the first thing we're going to do is actually create that LoRa configuration. I'm giving it R8 just by default. They say 8 is a good place to start, and then you can kind of play around with it later and figure out what you want to do. And then we give it the target modules. These are exactly the same projections. I'm giving it all of them just so that my training is as good as possible. If you had a smaller GPU, you'd probably not want to use all of these layers. You might want to use a smaller R. These settings will depend upon how well your model learns, how difficult the task it is, and how good your compute is. And I'm also just providing that the task type is causal language modeling. But that's it. That is my LoRa configuration. And then I'm also going to load my data set. It's the same data set that we just took a look at. I'm just doing from datasets import load dataset. This is a Hugging Face library as well. I'm loading the dataset by just giving it the name of the dataset. And then I'm also mapping that to my GPU and I'm tokenizing it. Questions so far?
Sorry, when I'm running this, when I run the quote imagine is, I just get the quote. I don't get Albert Einstein or the follow on. Did I need to do something?
No. So as you might remember, these models are not deterministic. They tend to kind of have that little bit of randomness to them. So possibly if you run it like a bunch of times over again, it might provide you with something different. It might not. I've also, whenever I've loaded a new notebook or like have a different GPU or whatever, these tend to be different. So you might see something entirely different, but what you are seeing is something that does not look like this, something that has quote author, quote author. So that's kind of where we're aiming for. We want to be able to provide it with a chunk of a quote, and then it returns the quote and the author's name.
And
So,
are we
so that
going
might be
to
a little
change
bit.
it? So right now I'm not getting the author. So you're saying that's what we're gonna try to
Right.
fine tune?
Yes. And so
Okay.
similarly, if you had asked this to do some sort of Python programming, it would probably not do a good job. But the idea is that we're going to do fine tuning on it using, in that case, it would be a data set that contains prompt and response pairs, similar to what we saw yesterday of Python code and output, or input and Python code. But the idea is we're going to try and make it better at this specific task.
Okay, thanks.
Cool. Other questions? Okay. So moving forward, now let's take a look at the actual training loop. So the main library that we're going to be using is TRL. This is also a very, very powerful library that pretty much provides you with built-in code, which you really don't need to mess around with it in order to fine-tune almost every single model that's there on Hugging Face. So as you might remember, we're going to have to first create that formatting function. This is similar to what we saw yesterday, that Gemma has a specific formatting function. So we're just formatting our inputs in a certain way so that they look like what Gemma is expecting. And now we just use the supervised fine-tuning trainer, SFT trainer. And we could theoretically use this right out of the box without changing anything, but because we're doing parameter efficient fine tuning and we're using LoRa, we're gonna want to ensure that it gets that information. So, oh, my runtime just disconnected. That's all right though. But the things that we're gonna want to provide it with are the model, the training data set, and a couple of arguments that actually configure how the training is going to work. Things like batch size, gradient accumulation steps, the maximum number of steps. This might also be known as like the epochs. The learning rate, floating point 16 is just saying that we're going to want to do this in sort of that quantized way. Logging steps, where we want to save the output, what the optimizer is, all of these things. If you're not familiar with them, don't worry about it. You don't really need to know what they are. But if you are interested, I would definitely encourage you to kind of maybe go look at one of the 3 blue, 1 brown videos on fine tuning. They really go into the details of what this is. But a lot of this is essentially just backpropagation and gradient descent. And then finally, we provided a PEFD, parameter efficient fine-tuning configuration. We give it that LoRa configuration that we made earlier, and we also give it the formatting function. That's the entire training loop. That's all you need to do. And then all you need to do is call trainer.train, and it will train for 20 epochs. On an A100, this took me 12 seconds. On a smaller GPU, this could take you several minutes. But that's the power of having a very, very good GPU. These things happen very, very fast. And this is also a fairly big data set. It's a very small data set. Yeah, it's 2,500 rows, but that kind of puts it into perspective. Like fine tuning does not really need all that much data. It's still like 2,500 rows is still a lot of data, but it's not like those trillions or billions of tokens that we were seeing for pre-training. You can get away with a pretty small amount of data. And then the only thing that you really need to pay attention to is the fact that the training loss is going down, which means that it is learning, its loss is going down, its error rate is going down as it's training. And we can see we started with a loss of 1.37 and we ended up at 0.06. So it clearly learned something. Looks good, but how do we know if it actually trained? We can ask it. So again, I have the text, quote, imagination is, the device is my GPU, my inputs are tokenized. my outputs, the model generates the outputs, and then I print it out, and it says, quote, "Imagination is more important than knowledge, author Albert Einstein." I do not know why it printed it out 3 times. It did not do this yesterday. Again, this is a very, very quick fine tuning. So this is not, the best fine tuning that you could probably do. You probably want a better data set. You probably want more epochs. You probably want more steps. You probably want to do a couple of different things, maybe even use a better data set. But generally you saw that, okay, now it's at least following somewhat of a format when it is outputting rather than just continuing on with another sentence. So there you go. In about 12 seconds, we fine-tuned a model from not following some of the most simple instructions to being able to somewhat do it correctly. And now you can kind of follow this exact same pattern. In fact, you will not need to change the code. You would only need to change the data set that you're providing in order to train this on your own data. And then if you wanted to, you can save this model and in its current state as Gemma 7B PEFD quotes. So now this is just a model object that you can upload to Hugging Face. You can use later, you can load later and use as you please. But that was a sort of crash course through doing parameter efficient fine tuning. Very simple. And it's kind of the exact same process for most training methods. If you weren't doing parameter efficient fine tuning and you still wanted to kind of follow this, all you would need to do is get rid of this line. And now you're no longer doing parameter efficient fine tuning. Now you're just doing the full fine tuning. All I did was get rid of the parameter efficient fine tuning configuration that I provided it with. And the SFD trainer knows exactly what to do with that now. Questions about any of this? Yes, epochs and steps are the same in this case.
So the math that Jesse was talking about on Wednesday was LoRa, correct?
Yes, correct.
So you're saying, and that was the whole point of that was to make it go faster. You're saying if you took that one line out, you could just hit run again and it would train it.
Yeah, it would do back propagation across the entire weights rather than just those selected like additional layers that we had in parallel.
Okay.
Currently, it's doing training only on those sort of additional weights that are being sort of added later on. But yeah, if I were to remove that PEFT config, it'll do back propagation across the entire thing. I will almost certainly run out of memory. And this will take a lot longer.
Okay. And did we assign, did we assign LoRa to LoRa config anywhere? Did we have to do anything to those parameters or?
Yeah, so we just created that LoRa config here where we provided R, the target modules and the task type. This is all you need to do apart from importing the LoRa config, and then we're just providing it here, and it's as simple as that. You just provide the configuration to the supervised fine-tuning trainer, and it knows what to do with it.
And wouldn't we always do LoRa config as opposed to full fine-tuning?
It depends. So for example, if you were working with a model that does not have a good baseline, say this wasn't, just telling the name of an author in a quote. And if this was something more complex, like for example, its understanding of protein binding or like DNA sequencing. And it just as a baseline has no idea what DNA sequencing is or what protein binding is or how any of that works. Just having to get it to understand some of those core theoretical concepts sometimes can be very difficult to get across in just a parameter efficient fine tuning. If your task is just like really out of field, you might want to do a full fine tuning. And also generally we saw that parameter efficient fine tuning, if the model already doesn't know the task somewhat well, it will probably not learn how to do it really well. So for example, if this was Gemma, or say let's say if this was the first version of Llama, it had no idea how to do Python programming. And then I did parameter efficient fine tuning on that. And I gave it that data set that we were looking at earlier yesterday. It will probably not learn how to do Python programming because it just has never seen something like that before. And so it really needs to develop those sort of understandings across the full weights rather than just like these extra layers. So yeah, it would really depend. The answer is it depends. If it learns well, I would always say, start with parameter efficient fine tuning, just so kind of get a baseline of, where your model is at. And if you still need a boost in performance that's just not just a little bit more, but like a lot a bit more, then I would say you want to do a full fine tuning.
Okay, thanks.
We have another question. What is the difference between LoRa and QLoRa? That is a great question. So the only difference is that QLoRa is quantized LoRa. So essentially that means that we're using a quantized version of the model. Everything is being done not in full floating point, but 4-bit. So things are just not going to be as accurate, and therefore the model will theoretically not learn as well. But that is another way we're ensuring that this fine tuning can happen on a single GPU easily and quickly. But if I were to not have this bits and bytes configuration and not have that PEFD configuration passed into the supervised fine tuning trainer, it will just do a basic full supervised fine tuning on the full model, and probably that model will not fit on this GPU. I have an A100. It might fit on an A100. I have an 80 gig A100. Yeah, so it'll fit on this GPU, but it will not fit on any of the free tier GPUs. Cool. I'll keep answering questions about this in the chat, but in an interest for time, and so that Abby can kind of get started, I'll just hand it over to you, Abby.
Okay, awesome. I'm going to share my screen. Okay. So we are going to be working out of notebook 3.4, which I will stick the link in the chat super quick. Okay, so similar to sort of kind of recurring theme here, anytime that we are working with these models and having to actually load them into memory and use them, is that these models that I'm going to use in this notebook are pretty big. So I recommend following along, not by running this. I think pretty much unless you do get access to some high GPU or high RAM GPU, you are going to not be able to put everything into the GPU memory, and your runtime will tap out on you. So I'm not actually going to rerun any of these cells right now because I'm afraid of my runtime dying, but I will be talking about kind of what we've set up here. And so if you wanted to explore doing this for your own work, I would highly recommend getting Colab Pro to have access to one of these higher runtimes or higher RAM GPU runtimes. Then maybe you could run this on your own, but like I said, for the interest of probably people don't really have Colab Pro, we're just going to talk about this notebook. So what I'm going to be telling you about is I called it fine tuning by proxy, but you'll come to see that that's a misnomer because you're really not fine tuning at all here. Proxy tuning is quite a scrappy, clever technique for getting fine-tuned-ish results of a larger model using a fine-tuned smaller model. So sort of to set the stage here, we have seen kind of repeatedly over the AI summer how fine-tuning models to get particular behavior is really powerful. But as like Umang just showed us, you can use these techniques that like fine-tune much less of the model. Like you can make this much kind of easier of a task, less computationally expensive of a task, and it can still be very computationally expensive. So in that last notebook, we had a Gemma 2 billion parameter model, so it's quite small.
fine tuning it on 2,500 pieces of data. And yes, on a GPU that did run quite quickly, like fine tuning is possible, but it is still quite difficult. And especially if you wanted to, let's say, fine tune a model that is very big, like if now I'm looking to fine tune Llama 70 billion, that is a large thing and a lot of effort to fine tune. So the whole concept behind proxy tuning is that there are instances where it may be possible to instead fine tune a smaller model, or maybe we have a smaller model that we have fine tuned. Small models fine tune great. They can learn really specific tasks really well. And we can use a smaller fine-tuned model to actually guide the knowledge of our bigger model and produce fine-tuned like results in a bigger model without ever fine-tuning it. So we get to kind of preserve the larger models, better, like the larger the model is, kind of the better it is at, reasoning, kind of complex thinking, those types of things. But we can sort of mitigate the issues that it has with doing a specific task over a small model that does that specific task really well. So that's the idea behind proxy tuning. I want to point out that this first link here is a really great resource that I've sort of taken the example that they've done here, the specific kind of question they're trying to get the model to answer, and the training that they are doing, or the proxy tuning task that they're doing, which is a Llama 7 billion to a Llama 13 billion in our case. And they have some great kind of explanations here. And then I will also point out, I put at the top of this notebook the paper. I find this paper to be quite readable. Sometimes papers are not very readable, but I think that this one really is. They explain in a lot of detail kind of the principles behind what they're doing. It helps that the concept behind proxy tuning, as you'll come to see, is actually very simple. And they do a great job. They have this really nice little graphic. They do a great job of kind of explaining what they're doing, and they do a lot of kind of rigorous testing. So odds are, if you have a question about proxy tuning, it is actually decently well answered in the paper, which also a lot of times is not true for papers. So two amazing resources if you want to know more about this. But so let's just get into proxy tuning, because we have still a whole notebook to get through. So like I said, the whole idea behind proxy tuning is that it's taking a fine-tuned model, a fine-tuned small model, and using its performance to guide a larger model. The way that you do this is by comparing that fine-tuned smaller model's performance against the non-fine-tuned version of that smaller model, and taking the difference in its performance and just directly adding that to the non-fine-tuned larger model. I'm going to actually reference this graphic because I think it makes a lot more sense in a graphic. So if you have, let's say, Llama 2 70 billion, and we're going to be doing this with 13 billion in the notebook, but in the graphic, it's 70 billion. Llama 2 70 billion has a chat version, which we just talked about today. Chat means it's gone through all of this extra training, which really are extra fine-tuning steps. So it still has a lot of its original capability, but it's been through this extra fine-tuning in order to be performant as a chat model, to answer questions and to interact with us well. So Llama 2 has, for every one of its numbers of parameters versions, there's chat and there's non-chat. So let's say Llama 2 70 billion existed, but no one has made Llama 2 70 billion chat. And you really wish they had, because you want to chat with this thing, but it actually doesn't exist yet. Well, the idea behind proxy tuning is that if you had Llama 7 billion original and chats, you can just take what the difference in their output is, because this is the same thing, except one has been chat fine-tuned. Add that to Llama 70 billion non-chat, and you'll actually get performance that's quite similar to Llama 2 70 billion chat. And it truly is that simple. Like, if you just take the outputs you get raw, you find the difference, you stick them onto the other thing. It turns out that what logits represent for a model is that you can just take that difference and add it in. It's correcting the probabilities that these models want to predict for the next token, or the logits, so it's not quite a straightforward probability yet, but you know what it wants to make the next token. You're taking what the difference is and you're saying, I want you to be more like the chat thing, so let me add that difference back to this thing, and that will make this more like the chat thing. And so it's really, like I said, this incredibly simple thing to do, but it's super powerful because you actually really do, like, you get performance similar to the chat version of this much, much larger model just by doing this. And so in the paper, they're calling, they're saying you have a target model, an expert model, and an anti-expert model, which I think the anti-expert is funny. Because the anti-expert is sort of explicitly really bad at the task, right? Like the unfine-tuned version of the small model is like, you're explicitly saying this is bad at doing this thing, and this other thing is good at doing this thing, and that's why you can exploit the difference. And I think there was a question in a chat, how do you get the fine-tuned? So you would have to have a fine-tuned smaller model. But the idea is that if you wanted a performant, really large model, it is way, way, way lower of a lift to fine-tune a smaller model than it is to fine-tune a large model. So you could fine-tune a llama 7 billion and then apply proxy tuning to a llama 70 billion and end up with a llama 70 billion that is more performant on your specific task, but you only ever had to train the 7 billion, because training a 70 billion would be a lot of effort. Okay, so let's go through the note. The code is actually really simple to do this thing, because like I said, it's really just subtracting some logits, adding them back in the right place. Bada bing, bada boom. So what we're going to be, the task we're going to be doing here, like I said, is going to be using 70 billion as our anti-expert, so the model that really is no good at this thing. 7 billion chat as our expert, so the one that has been trained to do chat, it's really good at it. And 13 billion is the model that we are going to be targeting to improve its performance. So make 13 billion more like chat 13 billion, even though we're starting with non-chat 13 billion. For all of these, you can find them on Hugging Face. If you want to run this notebook yourself in future, you do have to like give Llama some information about yourself, your contact info, in order to get access to these. I have access to the models, and I think that you only have to request access to one of these three, and they'll give you access to all of the Llama 2s. Okay, so then we install a couple packages that we need. We're gonna log in to Hugging Face using our token, and then we can get started. So the way that I am loading in the models is through this pipeline, which I believe we may have seen the pipeline functionality from Hugging Face, but really it just sets up the model in a really simple way so that we can just do a forward pass and see what we get out of these models. So we're loading the chat, the regular, and the 13 billion. This will take some time, and this will take a lot of GPU RAM to load all of those three models at once. So that's part of why you really do need quite a lot of GPU memory just to kind of be juggling. All the three models do have to be kind of loaded in at once in order to compute all the things we have to compute for this. But let's see what we get on a test problem. So what I have here is some input text, which is if I have 5 apples and I eat 2, and then I find 4 more on my way home, how many do I have? So this is very clearly a question, which is meant to be answered. And as we can expect, 7 billion non-chat will probably not just directly answer the question for us. So here I'm just passing that input text into the pipeline that I set up for 7 billion, and I'm printing what I get. And it says, if I have 5 apples and I ate 2, but then I find 4 more, how many do I have?
it actually does say answer 7, but that's not because it's answering. That's because it thinks that it's setting up some sort of like coding problem where like this is the full thing, is like this is a question and then the answer is like how to code that up. So it's not having like a chat behavior where it is trying to answer the question and explain how it came up with the answer. It's more, and this code is not good. Count up, like, yeah, but it's making an attempt to sort of finish what it thinks I'm trying to say by interpreting my input of a question as being, yeah, some sort of like homework assignment maybe or something. Okay, but then we can ask Llama 7 billion chat the same thing. So we're putting in the same input text into its pipeline. I thought this was really cute that it makes itself a multiple choice test that it then answers. But here it is going to answer our question, and that it is going to give answers, tell you what the answer is, and then give you an explanation. So it is directly answering the question that I have asked, which is how many do I have? It's going to explain to me why I would end up with 7 apples. So again, these are really small models. So sometimes the way it decides to answer questions and this behavior is like kind of weird, but that's what you get out of a 7 billion parameter model. But yeah, so we treat 7 billion as an expert in question answering here, right? So it is a model that's already been fine-tuned, as we've talked about, and it's able to answer questions. If it gets a question, it knows that it's supposed to provide a literal answer to it, versus 7 billion doesn't. And 13 billion doesn't either, right? 13 billion, as we've already discussed, has a chat version and a non-chat version, and we're taking the non-chat version. So it would probably have a really similar behavior to this. And actually, spoiler alert, I guess, I ran it towards the bottom to show as a comparison, but we can look at it now. So the 13 billion non-chat version actually does quite a similar thing to the 7 billion non-chat, where it sort of thinks that this is like some code that it has to put a bunch of paragraph markers in and export it as an app and all that. So not answering our question directly, indirectly ending up answering our question, but not because it knows that it's supposed to be. And I found this really funny that actually it does the math on the question I asked correctly, and then it makes up a second question for itself and does the math wrong on that one. So yeah. Okay. But let's proceed. So this function here is really the entirety of proxy tuning, because like we discussed, proxy tuning in itself is really simple. Basically, everything that's happening in proxy tuning is happening here, where we're taking each of the models. So the one that we want to change the logits of, change the output of, to guide it more to be like chat. Then we take the model that we know is tuned on the thing and the model that has not been tuned on the thing. And all we do is take the target, the model that we want to edit, and we add to it the difference between the tuned versus the base logits. And like I said, the logits, they straightforwardly just kind of operate like that. That then if you treat this new set of logits as kind of the logits we want out of this proxy tuned model and figure out, turn them into a straightforward probability, select one of those, the way that all of our models kind of do a forward pass to generate the next token, then the next token that we get is different because we've adjusted these logits based on this behavior. And so we run this in an iterative process. So this is happening in a loop where we're just going over and generating every single new token in this way. Because remember that the way that these models are running is that every single new token is based on the context, which is everything it has so far. So both of our question plus what we've started to generate so far. Every time we generate a new token, we're basing it off of like all of that we've done so far. And so we're just running this forward pass, running through generating a new token, and we're basing it off of all of the previous tokens that we've now generated in a proxy tuned way. So all of the output is kind of being adjusted according to this difference. And so we run that through up to some maximum length that we've specified, adjusting the logits, getting whatever token it is, adding that into our generated text, and then we're going to just return generated text, which should approximate 13 billion chat in this case. And so to call this function, we're going to, which I've called generate proxy tuning, we're going to just specify what those three models are. So in our case, there are these three pipeline models that we've talked about. Specify the tokenizer, which just, of course, tells the model kind of how to treat the text. Give it that piece of input text. So we're reusing the input text that we used here. So we're asking that same question. If I have 5 apples, I eat 2. Find 4 more. How many do I have? And I set a max length to 60. And you can see that the proxy tuned generated text is great, right? I asked it this question and it answers it. You have 5 apples initially, then you eat 2, so you have 3 apples, then you find 4, so you have 3 plus 4 is 7. So it goes through all of the logic. It goes through better, like this answer is better than 7 billion chat, actually, because you're taking a little bit of advantage of how 13 billion is just a little better in general, but now you're adding this ability to chat onto it. So that even though this never used 13 billion chat, you actually get better results than 7 billion chat, which had this kind of weird formatting to its answer. But this was never a chat model at all. So it's incredibly cool that you can just do this little thing with the logits and like you literally get much better behavior from this large model, and you get to keep the advantages of that larger model by just making this little adjustment. And so, yeah, I did a little bit of a spoiler, but like if you compare this to the 13 billion chat, you get a similar answer. This I thought was also really funny because I ask it the question and it starts by saying you have 6, and then when it explains itself, it arrives at 7, which is the correct answer, and the explanation is the same as above, but it just decided to say this first. But like we keep saying, these small models, they just, you know, they have their quirks. But again, keep in mind that this proxy tuning was an adjustment on a initial prediction that was more like this, right? Which was this like weird trying to turn it into code, whatever. Versus now we have generated text out of our 13 billion non-chat that really closely matches 13 billion chat, and you're getting the really similar performance just by doing that little trick to the logits. Okay, so that really is the whole concept behind it. That went really quick because we didn't run any of the notebook actually, because we don't want to run out of memory. But are there any questions about this?
Yeah, hi, Abby. This is Mohsen. I had a couple questions. It seems like, just to clarify, we're just trying to make it so it's chatting and not, like in that example, putting out code. We're obviously not trying to make it do math correctly in this example. Like we're not trying to get it to do the math, the 6 plus, or the whatever, the 5 minus 2 plus 4.
Yeah, I mean, yeah. So in this specific example, yeah, the fine-tuned versus the original, the difference is its chat abilities. You could train it, and I think that in the paper, one of the tasks they do is training it to be better on like a coding thing. So I mean, you could train it for specifically some other specific task. But the fact that like the math ends up being better here is maybe, if anything, a function of the model being larger, because larger models just sometimes are better at math because they just do better like reasoning internally. But yeah, no, there's no like specific training to be good at math. It's more training, yeah, to just answer the question.
Okay. And that paper is like last month. So this is like sort of real cutting edge stuff.
Yes, this is like a brand new, yeah, which is very cool. And like I said, I mean, I just think it's so cool how
Simple. Yeah.
simple it is. Yeah, it's so like, I don't know, you read the paper and you're like, that's so obvious to do that, but also it's obviously not. Yeah.
Hmm.
Are there any other questions about this? And yeah, want to point out, just in case anybody did not see Umang's comment in the chat, because it is a great point that, yeah, the underlying assumption of this whole thing is that this tokenizer is shared, so that like the way in which you're embedding everything and decoding everything with the tokenizer is the same. So yeah, it works great for Gemma 7 to Gemma 70, llama to another llama, because they all share that underlying tokenizer. Okie dokie.
It just seems like, all of us in this room could have figured this out. And it's amazing that this type of stuff still exists. That gives us hope that we can add value here.
Okay, well, I will stop my share then. And I guess we can just take questions about anything that has happened today.
Any questions that y'all have about today, or I guess the rest of AI summer that we've been through thus far? Well, as we're going, oh, Esra, I saw you unmuted.
I did, yeah. During yesterday's AWS session, there was mention of telling the model to stop and think. If I'm not mistaken, there was something to the effect of telling it to, like in real time, process it like how we think about things. Am I mistaken?
Mm-hmm.
Do you remember this?
I think was it a discussion about chain of thought prompting?
Okay, Abby said yes, so yes.
I think so, yeah.
So could we prompt it to do the same thing when wanting it to calculate something, just saying, don't give, like, take a moment, please, make sure you're giving accurate data or an accurate response?
So I think it might be the less of the take a moment, but maybe more of the way that you present, like almost the few shot examples. Like that's not exactly what it is, but the way that you present the examples to it, like the let's think step by step thing. I'm trying to find like their resource on that because it was really good.
Yeah, I'll definitely add that sort of forcing this model into a space where you ask it to sort of think through the response that it's about to give you somehow works really, really well, especially for super complex tasks. For example, the coding manual that I was talking about on Monday or Wednesday, where we have 500 different categories and we're asking a model to like, categorize this one specific chunk of text into one of the 500 categories. That if in for certain sets of categories, if we asked it to explain why it's categorizing it in that way, it would almost always change the category that it's categorizing it as, because it actually kind of thought through it and was able to come to a better conclusion rather than just out of the box doing sort of what's the next best token essentially. But yeah, chain of thought reasoning can be very, very powerful, especially for more complex tasks, because it really forces the model to kind of logic its way through to a conclusion rather than, I don't know, somehow go to the most obvious one, which is really weird to talk about because these models are thinking, but I guess they are thinking.
Yeah, I think it's definitely, yeah, like Umang's kind of saying, it's less about the take a moment to think, like actually the using the extra time, and more about the like, if you force it to generate an explanation, it's like the tokens it generates in sequence of an explanation, like better come from what came before than like just generate a token that's attempting to be an answer, you know? And I mean, you kind of just saw that, yeah, in the example that I had, right? Where it like says the answer is 6, and then when it has to explain itself, the answer is 7, because now that it's been forced to see all of the steps up to there, it like is better able to figure out
Right.
what
Yeah,
the final.
especially with math, it will always do better if you kind of ask it to explain why it's doing the math a certain way, because LLMs are notoriously bad at math. Because at the end of the day, if we go back to like day one thinking about tokenization, the tokenization for the number one isn't actually one. It's like 6,452. So like once it starts kind of doing math like that, you can see where it might start going wrong. So for math, chain of thought reasoning is generally really, really powerful.
Thank you.
I kind of see it. It seems like you're almost making it create its own few shot example. Like here,
Yeah,
give us a like what Abby said. It gave here you gave an answer, but you know what? Let's feed that back into the context and see if you can come up with a better answer.
Yeah, chain of thought yeah, few shot prompting also kind of works very similarly because you're essentially putting more into the context that's guiding its next token far better than what it would otherwise.
And I think also some models are trained very specifically on chain of thought prompting. So it's like a part of the model training that they actually go through. So when you ask it to like think step by step, like it remembers what that is. And while we are asking questions, I think in preparation for next week, we would love to know, as you are developing, what kinds of problems that you are running into while coding. We want to see if there's any resources that we can provide or examples that we can provide that will like kind of walk through what it would be like, or ways that you can approach using generative AI to support your coding efforts. So if you have any questions there, if you think of anything over the weekend, just, shoot us an email or you can drop it in the chat. Just let us know and we'll be happy to provide some examples of maybe ways of resolving those issues.
Would be helpful is like you've introduced us to a lot of tools. Maybe a quick email that says, okay, this is LangChain. These are the 2 or 3 things you would use it for. This is LM Studio. These are the two things you would use it for. I don't know if that's maybe it's putting it into a box too much, but like sort of we've gotten access to a lot of tools and my head's sort of spinning. Because you go to their pages and it's like, oh my God, I gotta go through all these docs to like just understand what it's supposed to be used for. I mean, you guys have done a great job getting us there, but once you guys are gone, I'm not sure I'm gonna be as motivated to like go through all those documentation pages.
Okay, gotcha. That's a good suggestion. Thank you.
To tag off of that, any resources on how to develop your model architecture, which would kind of be influenced by what Mohsen's asking for, would be helpful.
Model architecture as in how you put together a full solution, or literally like how the LLM, like you want to change like the number of layers or something like that?
Yeah. Yeah, how to structure it, the LLM.
The LLM itself?
Mm-hmm.
Interesting. Okay.
I came across one tool, I think it's called Crew AI. Are you guys familiar with that at all? No. Deep learning has a little thing. It seems like it's dealing with agents and stuff like that. So anyway, I was
Ooh.
looking at it. They have a little short course, free short course on deep learning AI that just popped up literally this week. And it seemed like it's dealing with agents. So I was curious if anyone had seen it.
I definitely will be looking at it though. Thank you.
Mhm.
All right. Well, I think that this is all that we have today. I guess we'll give you 4 minutes back to your day, but please feel free to come into office hours and discuss whatever you would like to discuss. So we'll start office hours now. And y'all are so welcome. All right, any questions?
Miranda, this one's for you. And I'm still understanding these concepts, but how would creating synthetic data in the environmental and urban planning field, in your opinion, be really helpful?
I've never really thought about synthetic data in environmental just because there's usually so much data. I
Yeah.
would say synthetic data is more useful where you don't have a lot of data or the data is private for some reason. So I actually haven't thought about it, but I'll give it some thought, and then if I come up with something, I'll let you know.
Sure, sure. Thank you.